Okay, so today I'm just going to be going over what I do in MolFlow and what it is, and like maybe why you should use it, or just give a brief overview of it. I use it mostly to simulate vacuum pressures in ultrasonic vacuum systems. So this is developed at CERN, and it uses Monte Carlo methods to basically find, depending on your outgassing rates and the materials you have in your vacuum, to find the base pressure. It's free to use, developed by these people, and it is still like actively maintained. So it's a lot better than just using like handbooks that you get from like Pfeiffer or Labeled or Agilent to calculate base pressures. It can be a lot more accurate, but it's going to be limited by like your outgassing rate data. So like how accurate that data is, and how well that actually reflects, your actual system is going to limit you on how well the simulation will work. But CERN obviously uses a ton of vacuum systems, and it's no surprise that this was developed here. So I'm just going to download it. I guess they do have it for Mac, which is pretty cool. But so yeah, you just get the zip. It's really small. And then you can just extract this file basically wherever you want. Just put it on my desktop. Okay. So, and then after that, you can just run the execution, molflow.exe, and it should just come up very quickly. So you can see this little molecule icon, and then this is your starting point. So I'll just go through like the basics of like what I would do if I'm going to simulate a vacuum system. You can use this for other things, but maybe I'll make another video. So in general, you're going to need some kind of STL file to import into here. You're going to want to make a simplified like geometry, because when this generates a mesh, if you have something super complicated in a really complex inventor file or something, the mesh is just going to be, it might not fail, but it's going to just be unnecessary for what you're trying to do. So like most of my designs will have vertices or facets that are like probably 1,000 or 2,000 for the entire system. So there's 2,000 facets in the whole system. More than that, it's fine. I mean, it'll take more computational time, and I just don't usually see a point. So I've already made like a simplified version of our vacuum system. So it has all of the walls, all the relevant internal items, and then it has the pumps. So I'm just going to load that geometry. Here we go. So final assembly. This is actually an older version of our current vacuum system. So when this pops up, I don't mess with the vertices or facets or anything like that. I just usually leave it as is, unless it made one that was really unsatisfying. So when it imports it automatically, so if this is the first time you've ever done this, the first thing you're going to want to do, or at least I do, is go to the 3D viewer settings. So you can get rid of the rules. I mean, it's mostly preference. I always put on the normals, so that means if I click on something, a facet, it'll have an arrow normal to the surface. I don't usually put on leaks. Sometimes I'll put on lines and textures. Textures are pretty important, especially if you want to see, the pressure on a wall or something at some point. So usually you should have that on. Okay, so after that, I select everything, and then I go up, and then I swap the normals, because for whatever reason, all the normals are like inverted from what I actually want. So now that when I click on, something on the outside of the vacuum chamber, it's pointing out, and if I click inside, you got to double click sometimes to get interior. So there's a facet on the inside of the wall, and you can see it's pointing towards the interior. So when this when you first start simulating this, at every time step, it's going to calculate based on all of the particles or all the material properties that you put in, whether or not something is going to desorb or be absorbed. So in the system, it's assuming molecular flow. None of the particles interact. The trajectories of the particles are like pseudo-random. So if something is going to desorb from a wall, whether it's a new particle or one that had previously been desorbed, it'll basically calculate the probability. Its trajectory probability will be random. So after that, so after I swap all the normals, I'll start to make a log. So I have quite a few. I have 5,000 facets. I'll make a log of basically where all of these are relative, categorized kind of by their material properties. So I don't think when it generates these facets, I don't really think it does it. It does it in a semi-organized way, but I always find this time-consuming. And anytime you put in a new geometry, you kind of have to do this. Is you have to just go through kind of one by one and say, okay, all of these structures from number 100 to 300 is all stainless steel, and then I'll just put that in like a notepad, like here. I'll say, okay, so then I can easily find it again. So once you go through and you categorize everything based on the kind of properties you want to assign to it, then you're kind of at a good starting point to put in everything else, to put in those properties. So I'll just basically make everything stainless steel. But if you did want to say, like, let's say 100 to 200 is not, let's say 100 to 200 is like titanium or something, facet number. You can options up here, so you can select by either already assigned properties that you've already assigned, or just by the facet number. Those are the two most useful ones, or like by all the property or all the facets that have some sticking coefficient. So the facet number is usually the one I use the most when I want to just select anything. So select 1 through 200. So this is like an RGA filament that I put in the geometry, and then this is like all of our experimental stuff down here. So you can also assign, like 500 to 700 like this. So they don't have to be all in a row. So so that's useful. I guess, let's see, I'll go through and I'll assign some pumps. So this orifice here is the ion pump we have in the vacuum system. It's also kind of hard to see, but there are non-evaporable getters in the vacuum system. And I can assign properties to those too. Usually those are at the end. So I'll assign some properties. Yeah, so the last ones. So all these I'm highlighting now are just simplified geometries of what the non-evaporable getters actually look like. So facet, well, not all. This is 541 to 585. Okay, so I've selected my non-evaporable getters. I don't want them to desorb. I could, but I'm just going to assign them a sticking factor. I just assign them 0.15. It's pretty much arbitrary. You can look at the manufacturer spec sheets. In reality, these getters are not like these solid rectangular blocks. They're very porous, and they have a large surface area. And the way I assign the sticking factor to take into account those geometric properties that are not actually in this CAD model is by increasing the sticking factor. So these are 1,400 liters per second each for hydrogen, but that was measured at 10 to the minus 6 millibar. So this is ultra high vacuum, which is 10 to the minus 11 millibar. So in reality, the pumping speed is probably going to be a lot less than that. So here, the pumping speed calculated it based on the sticking factor, and that's 1,000. That's fine. I mean, if I wanted to be more precise, I could put 12 or 11. Now it's about a quarter of for all of these pumps, it's about a quarter of what the specified manufacturing pump speed is, which is probably a good estimation for ultra high vacuum. So now I have some pumps that I've assigned. Some sticking factor 2, that's good. I still don't have any vertices that are desorbing, so that means that nothing's going to happen if I run the simulation. So I'll assign a bunch of interior surfaces to desorb. Here. Okay, we'll go just arbitrarily 4,000, 4,100. So that's some interior surfaces. I just clicked uniform. If you want to get more complicated, you could do something like that. But if this is stainless steel, we could do I think it's 2e minus 14 or something. No, per centimeter squared, my bad. 2e minus 14. So now, you can either do outgassing rate per area or just a straight outgassing rate. I just happen to know the rough outgassing rates per area of some heat-treated stainless steels. So I'll apply that. So now it'll desorb. I didn't put any sticking factor for outgassing stuff. Usually, you could. It'd be very low, so I think it's negligible. I don't think you actually need that. You can also assign, temperature to things, which I've done, because desorption is somewhat exponential with temperature, so that can be important. But for the most part, there's no hot gauges near our experiment, so I don't really care. I have ran simulations where I increased the RGA filament to simulate what it would look like if our RGA was running at 70 C or something, and it doesn't really have an impact on our base pressure near our experiment, so I just ignored it for the most part. So now that we have some vertices that are desorbing and we have some vertices that are pumping, we can actually run an experiment. I'll assign some pressure as well. So, or some pressure textures, so you can actually see the pressure change. I'll just assign that to the same interior area. So I'll enable texture. You need to give a resolution, or you need to give what the texture is based off of. Usually, I just do count reflection if I'm looking at something that is that if I'm trying to get the pressure of something, you could count absorption or desorption, but usually I'm just trying to get the pressure at the wall. So then it'll force remesh. That's probably too high. No. Yeah, that's going to be huge. I better delete that. Okay. Let's just restart that. Okay, now I need to load in everything again. Okay. Oh. Well, this actually already has a bunch of, this is an older one. Okay. I'll just load the geometry in. Okay. Some millimeters. Swap normal. So once you get the hang of it, it's a lot easier. It's a really simple program, but it's incredibly useful. And it's really awesome that these people actually have released it for free. Okay, so I'll assign desorption again. And then I need to also assign a pump again. Okay. Okay. So now we're back to what we had before. Some other important things. To keep in mind is what the molecules you're actually simplifying, or molecules you're actually simulating. So right now it's at 28, which is nitrogen, so that's fine. You could do hydrogen, which is hydrogen molecules, which is going to be more, it's going to be a better representation of what's actually at ultra high vacuum. So there's really not much nitrogen like at all. So, okay. Now I have I have something pumping, I have something outgassing, and I have some textures enabled, and I changed the gas molecule to the correct gas molecule that I want. So let me enable the textures again, 10, see what that does. It's fine. Okay, so you can see they're all white. That's good. That's because we have the texture view enabled, which is important. Well, now they're black, but okay. So now we can begin simulating. So each vertex has, the amount of times it's been hit by a particle, the amount of times something's desorbed, the amount of times something has absorbed. If you don't assign any sticking factor, you're going to get no absorption. If you don't assign any outgassing rate, you're going to get no desorption. And then you can kind of sort those. So we do have some leaks, that's fine. That's just a very small amount somewhere where my geometry is not like totally perfect. But again, this is just a simplified version of our vacuum chamber. So then once I have this stuff running, I want to actually look at the base pressure. I go to texture plotter. So you can export all the properties on these vertices also, but if I'm like just running the simulation as is, I'll look at this. Usually I put logarithmic scale, and then I'll wait for it to converge. It converges generally pretty quickly compared to like most simulation tools. Again, it's just pretty simple Monte Carlo program, so it's not like solving some partial differential equation at every vertex or something and keeping track of it at each time step. It's less computationally intensive than that. So our outgassing rate for this whole chamber is like really, really low because I only selected part of the wall to be outgassing, so we're getting a really low pressure. You can see the yellow is about 2E minus 15 millibar, which is, I don't think, obtainable in room temperature systems, but that's fine for just showing people how this works. And then there's green, so obviously the pumps are up here if you can't see them, and that's why this is lower pressure. And then down here is where it's slightly higher pressure. So you can set the ranges of what you want this to be right here, which is useful when it's converged. Then you can export these. That's basically the majority of this. I mean, there's other things in the vertices that you can use, but it's relatively straightforward. Most of the time I just will wait for it to converge and then export the data from the vertices. So yeah, that's basically it. I guess I can show a different example. Yeah, I guess I can do that. Here, I'll show an example of one I've actually MolFlow. Oops. Okay, so this is one that I have like all the assigned properties done, and I've already ran it for a little bit. I probably need to change the texture plotter scaling. Yeah, so just quickly go through what's on this chamber. There's a titanium sublimation pump that's supposed to be over here, but it's not being simulated. There's an ion pump up here, and there's two NEGs, which you can't see really, but they're in here. And then this is where all of our gauges and diagnostic tools are. And then this is our experimental chamber down here. We have re-entrant viewports. What's actually highlighted with this texture is our trap. And the trap is really just like in this small area, but I'm just trying to get a relative idea of how the pressure here, what the pressure is like here. This is a big zero insertion force socket that the trap slots into. So it's actively running. I don't have any temperature dependence on the RGA up here or anything. And it seems like if you just look at the texture, we're at we're near 2 to 3 E minus 12 millibar. So yeah, about 3. So that's pretty good ultra high vacuum pressure. This entire chamber is titanium, so it has relatively low outgassing rates. But this is a decent like solution for our specific system. But to get this, I had to go through, basically all 5,000 of these and assign the correct properties. It doesn't take that long. It might just take like an hour, and then once you do it once, you're done. So it's not so bad. But if you keep making new geometries and new meshes and stuff, then you're gonna have to keep doing that, and that's just gonna be a little bit time consuming. Yeah, so to recap, MolFlow is just a tool you can use to simulate ultra high vacuum systems. It's basically simulate any system in the molecular flow regime. That's why it's called MolFlow. You want to make a simplified geometry that you can of your system that you can import easily, and then you're going to want to reverse all of your normal indices. Once you've imported it, you're going to want to generally click on textures and normal in your 3D viewer settings. You're going to want to go to advanced, or you're going to want to go to simulation and get the right gas molecule that you're trying to simulate. So if you have pumps that only pump certain types of species, there are certain species of gases, you can use this. And then once you have the right input for what you're trying to simulate, then you can go through and assign properties to all the facets in your system. And again, those outgassing rates are going to be kind of your limiting factor and what's going to stop you from getting to a certain stop your certainty in your simulation, or limit it at least. So then once you've assigned the desorption and the sticking factors for basically all of these facets in your system, you can start the simulation. And I don't have a specific, I just run it generally for a few hours. I don't have a specific way of calculating how well it's converged, but it does converge pretty quickly. So it shouldn't take very long. You're going to want to limit leaks if you can, but that's okay. Maybe I clicked the facet that was interior or exterior or something. And then your selections is kind of how you can easily get to different facets and change their properties. And the texture plotter is what you can assign the scaling to, so that when you have assigned texture to certain items with this advanced area, that you can accurately or more easily see what the pressure is there. And then you can also export these textures and facets, so you'll have exact numbers and desorption, everything you need. But yeah, so I'll go through one more example that's not an ultra high vacuum system. and then that's basically all I've used MolFlow for. But again, it's a lot better than just using like an ultra high vacuum handbook, because I mean you'll get similar results like I did, but it's just going to be a little bit more accurate, I think, assuming that you have good outgassing data.